Couple quick announcements. Office hours coming up on Monday. Canvas quiz is due 5 p.m. today. At that point, you'll also have Canvas quiz 2, the dummy one, so you should have that to practice if you want to go through Canvas quiz 1 and Canvas quiz 2 in multiple iterations for other material. Apologies last time. The sample midterms are up and they should be fully accessible. I hadn't had them released last time, so definitely those are all up for you to access now. End of today is the last time for your submission for please submit a question up onto Piazza. We had some good ones that are on there. Please, if you have any other last minute ones, happy to look at those. Reminder, Monday's going to be video. I have to go meet the health minister, so won't be there for that particular one. TA tutorial is on Tuesday, day of the midterm. Please be nice. I know it's going to be a gong show. Midterm 1 is going to be in the evening, 6 p.m. in chemistry. That's B150 and 250. I will put up the final names this afternoon, but roughly all I have to do is count how many people are writing where that sort of 50% based on last name sits. So I'll put that one up there. Again, not the end of the world if you happen to go to the wrong room. Reminder also about the midterm. We start at 6. You're going to write for about 75 minutes. We pause. You guys get to reorganize, and then we have the group portion after. Group portion is fully optional. You do not need to do it, but it's a good chance for you to work through the problems that you've been given as a team and get sort of some feedback instantly on the midterm. So today, we're going to go through a quick review of all we've done up until now. We are in lecture 15. So, and I'm trying to map this out over roughly what did we talk about during what lecture, so you've got a bit of a guide. So remember, going all the way back, we started off by talking about the carbonyl group, and we focused on the first nucleophilic additions to that carbonyl. Remember, this is where we're laying down the principle that starting off with the carbonyl, these are electrophilic compounds. Because they're electrophilic compounds, we're going to be bringing in different kinds of nucleophiles, and all of them are going to be doing this kind of a sp2 to sp3 kind of transition, right? We're doing an addition of some species to this compound. All the stuff we do is talking about this kind of transition where either we're going back to the carbonyl or we're going carbonyl to the addition complex. And it's about what kind of nucleophile and what kind of electrophile do we have to pair together to get these reactions to work. So we're starting to break down things like, do I need to activate the carbonyl? How do I bring them together? The first one we did, the cyanohydrin formation, was the first example of things, okay, I can take Grignards and attack carbonyls. Those are strong nucleophiles to a thing like an aldehyde or a ketone. But if I have something like a simple amine or a cyanide, things where we've got less nucleophilic components, now we may have to activate those species. So we have to bring in protonation of our carbonyl. So this is where carbonyl activation bridge is over. We're saying that I have to somehow modify my carbonyl in this kind of a state first to make it more electrophilic in order for the nucleophilic addition to happen, right? Then we start bringing in additions of alcohols. This is where we're taking carbonyls and we're hydrating them, where we're bringing in alcohol to make our what? There are 2 functional groups that we should be able to make from an aldehyde or a ketone. We form our, with alcohol additions, they're called our hemiacetal and hemi, and then we can go all the way, those become our acetals and ketals. So that's our lecture 3. These are additions of molecules to form up these kinds of compounds, RH or R across both, right? Remember, we use these primarily as a way of hiding carbonyls for other reactivity. What is more reactive, an aldehyde or a ketone? Why? Sterics and hyperconjugation. That's the major one. So if we had an aldehyde or a ketone and I didn't want it to react yet, this is where we bring in protecting groups. Protecting groups is that molecular waltz where I can hide an aldehyde or a ketone, the carbonyl, as an acetal or a ketal temporarily, and I can release it back to my aldehyde or ketone. It's a way of sort of hiding the reactivity as a molecule like this, which is no longer electrophilic. It can resist things like Grignards. It can resist things like base. Acids are what we use to pretty much form or unform them. Then we move into lecture 4. We're talking about the nitrogen equivalent. So we talked about oxygen as nucleophiles with ketones and aldehydes. Nitrogen as nucleophiles with ketones and aldehydes. These are our imines, the oximes, the hydrozones. What does a hydrozone look like? if I was a ketone, what do I need to form a hydrazone specifically? Say one more time. 2 OH groups? Hydrazone, there's something, yeah. NH2, NH2, exactly. This is hydrazine, something like that. Hydrazine reacts with a ketone or an aldehyde to make double bond nitrogen NH, right? It's the nitrogen equivalent of our imine. This imine, or this carbon double bond nitrogen, is the common thing in this core feature here. Warping ahead, we'll come back to it. But remember, this hydrazine, this step here, this is the precursor to one of the most other reactions we start doing later on. Enamine synthesis, the specialty there is they're just like, they're in the same family as these imines, but what's special about the nitrogen we use to make enamines? Yeah, if I was to take aldehyde or ketone, and I use a primary nitrogen, we're pretty much going to get, that's imine territory. Secondary nitrogens are necessary to make my enamines. Enamines have this characteristic where we both have the double bond alkene and our imine. That's why we're saying the enamine, it's amine-like, and ene is referring to the double bonding character here. So this is also where we're doing something else. There's one more feature that matters about this. To make an enamine, yes, I need a secondary amine. What do we call this center right here? This would be, let's say, that center right there. That carbon has a special name. It is the what carbon? It is the alpha carbon. We have to lose a proton from there in order to make a double bond. Otherwise, we've got overhybridization, right? So that's the second thing you need to make these enamines. Now we've done oxygen as a nucleophile with ketones and aldehydes. Nitrogen as a nucleophile with ketones and aldehydes. Olefination is just carbon as a nucleophile to ketones and aldehydes. So instead of carbon double oxygen, carbon double nitrogen, now we're doing carbon double carbon as the bonding formations. So this is where we introduce the Wittig reaction and HWE reaction. What's the difference between these two? If you had to sort of say the outcome of them, why do we have this pairing? They're both making something where I'm taking, let's say, an aldehyde, I'm using some type of nucleophile, and I'm making an olefin product. So let's say I drew this, and I'm just going to use sort of generics here. I know it's not fully descriptive. But if I had a molecule with a presentation that looks like this, what kind of reaction am I probably using? It's the geometry of your products that matters, right? So your HWE is forming something where reasonably big stuff goes across each other, versus if it's Wittig, we're trying to do something that looks more like this. Big stuff, same side. Everybody has practiced molecular patty cake, right? Right? This is all possible because your nucleophile, your electrophile are planar. Your two species come together, and it has to come together where the carbonyl and the carbon phosphorus are 180 degrees to each other. Your thumbs are your bulky groups. When you're talking about Wittig, these two species come together, your thumbs bulky groups are opposite, and then it gets tricked into, oh, look, they're on the same side, because we have to rotate the bonds around in order to get elimination, right? We go through the four-membered ring for that phosphorus-oxygen elimination. Horner-Wadsworth-Emmons, yeah, you can add this way, but what makes the Horner-Wadsworth-Emmons different? Why is it different? Yes? The first addition, you have a stabilized nucleophile with Horner-Wadsworth-Emmons. It means that that addition, in the case of Wittig, first one, you make the more stable one, you're done. You're locked in. Horner-Wadsworth-Emmons, you can make the stable one, tries to do the elimination. Oh, this was a bad choice. I need to go and reconsider my major. I'm going to slip up around and be a chemist. This is so much better in the long term, right? So it has a reversibility because the nucleophile is something that we can actually reverse. Then we bring into, now that we've got this ability to make carbon double bonded carbon, we can start talking about tautomers. Tautomers are talking about keto-enol. This is where the position of the hydrogen, now talking about the alpha center, matters. We can have two different forms the keto tautomer, where the double bonding is set up like this, and we have hydrogens over here, versus the enol tautomer. I'm going to draw it like this, where we have double bond this way. Now, as I've drawn it, did I do something wrong? What's wrong? Yes? I used a resonance arrow. This is not kosher. Do not do this. This is an equilibrium because I have to move a bond to get over here. Tautomerization is not resonance. The stabilization of the intermediates, yes, we use resonance, but since I'm moving a hydrogen from the alpha center up to the oxygen, this is hydrogen bond exchange. This is a reaction. Now again, in this case, most of the time, your keto is going to be your stabilized form. Enol can be stabilized, but give me two examples. Give me two examples of molecules where the keto, or the enol form, let's say, is stabilized. Yeah? So maybe like that? This magic, like this one for sure, right? Up here, this is phenol. This is a case where I could form this guy, right? Where I'm promoting the hydrogen down here. That just comes at the expense of your aromaticity. You have to pay aromaticity, break aromaticity, to make this one. So in this case, the enol form is going to win. Most of the time, your keto form is going to win. That's the big one. I'm not going to give you the second one. Don't worry. Focus on that one. Then we have hydrogen deuterium exchange and halogenation. These are the first time we're doing reactions at the alpha center. This is where the exchange, we're doing chemistry where this intermediate conversion between our keto and enol different tautomers, we're basically taking advantage of. So this is a case where if I had a molecule like this, and I have my hydrogens, HD exchange says over time, if I took, let's say, OD minus in, let's say, D2O, I'm going to make a molecule that's going to slowly exchange those hydrogens with deuteriums. So this would happen if a single exchange would have happened. In the molecule I've drawn, how many hydrogens total can exchange with deuterium? There's a total of 4 in this one. What we're doing is we're saying that these centers, whatever center here or here, goes through under basic conditions, I am making my enolate. It's making a molecule like this. So what we're doing is we're evaluating centers and saying if any of the hydrogens, if I was to deprotonate it and it forms a negative charge that is resonance stabilized to my carbonyl, that is a center that can undergo hydrogen deuterium exchange. So in this case, both of these centers, these both alpha centers, are possible. But remember, anywhere else through the molecule where deprotonation gives you a resonance stabilized anion back to the carbonyl is in play. Then we start talking about oxidations. This is where we're done with things like ketones and aldehydes. We're moving up in oxidation state from our carbon double bonded oxygen, something with only 2 heteroatoms on one carbon. We're moving up to something with 3 heteroatoms. So this is where we start learning about both reductions and oxidations. The first one is a transformation called reductive amination. This is where we're transforming something like an aldehyde into an amine where we've added this hydrogen in to that center. So we've one transformation, let's say we've already started out at a higher oxidation state, and we're both forming a carbon-nitrogen bond and installing a hydrogen at the same time. There's something special. There's a reagent that we introduced at this one that allowed this to happen. What's the other reagent? So in this case, I would, let's say, have my NR here. I have my aldehyde. I have my primary amine. What else do I need as far as my conditions to do a reductive amination? NaBH3 CN. That's sodium cyanoborohydride. Think of it as slightly more stabilized sodium borohydride, right? This is a reaction or hydride reducing agent that's got a bit of stability built into it. Remember, that is different because that hydrogen there is the one that's being installed as my reducing agent. That's the center it's being added as my H- equivalent. And it's only special. It actually reacts only with one kind of functional group. What's the rule that we gave you? Sodium cyanoborohydride is the tamed down version of a hydride reducing agent. It only reacts with what type of functional group? Not imines, iminiums. We need specially activated nitrogens. We're looking for something like this. The iminium, remember, when you mix these two guys together, they're going to form iminiums as an intermediate. That intermediate under these reaction conditions is specially activated for the reaction to complete. So we've targeted this as a combination where, yes, I can do my condensation reaction. The condensation reaction makes my activated iminium, and I have a reducing agent which is specially ready to reduce that activated species. Then we talked about our two ways of doing the global reset. This is how we take carbonyl compounds and turn them into simple hydrogens. It's a way of completely deleting out the carbonyl. Wolff-Kishner and Clemenson. What's the special thing? Wolff-Kishner works under what kind of conditions? Acidic or basic? Basic. Clemenson works under, and that's why we use them selectively depending on what's in the rest of the molecule. Wolff-Kishner is really useful at getting rid of carbonyls, but if your molecule has a functional group that is sensitive to a base, not your choice. Same thing, Clemenson will delete that carbonyl, but it's under acidic conditions. If your molecule has a group that's sensitive to acidic conditions, not a good choice. What is a functional group that might be sensitive to acidic conditions? More specific, diol protected, it is I think you heard it here, ketal or acetal, right? Ketals and acetals are in place to hide a carbonyl, but they will pop open with acidic functional groups. So usually we don't add those. What's this functional group that might be sensitive to strong base? Esters, yep, that's a good one. What else? Acid halides, those are substitution, elimination problems. Yep, absolutely. Anything else? Carboxylic acids. Acid-base chemistry might come in. Yep. Okay, up to lecture 10, this is where now that we can make carboxylic acids, we want to start reformatting them into different phases, right? So this is where we introduced how we make carboxylic acids. We gave you these four kind of core reactions. These are oxidation reductions. This is where we're bringing back things like chromium oxidation reduction, right? This is where we're doing from an alcohol up to an aldehyde up to a carboxylic acid. Those are all possible. And again, that means it only works with primary alcohols to get to carboxylic acids. Oxidations of secondary alcohols only get you as far as ketones. Nitrile hydrolysis, this is where you have your C triple bonded N, and you have both acidic and basic versions of it. Which one did we say is productive? Which is the one that you probably are going to use around the lab? Acidic hydrolysis or basic hydrolysis? Acidic. Why? Yeah, under basic conditions, you're going to stop at the amide. Acidic conditions, you go to the amide and eventually all the way up to the carboxylic acid. This is where, remember, what you're doing is you're taking a nitrile. Effectively, what you're doing under both cases, you're adding water to this nitrile in the form of either hydroxide or protons, and you're getting to intermediate that looks like this. That amide is just the addition of one molecule of water, but notice the same oxidation state. That carbon right there is carbon attached to 3 heteroatoms. In the middle, it's carbon attached to 3 heteroatoms. You've just changed it from oxygens to nitrogen. The next one, to get it all the way, you've got to do another hydrolysis, replacing this guy with your carboxylic acid. Basic conditions get locked up here. This gets much harder to do under basic conditions. Acidic conditions, this is now possible, right? If it's acidic, and this is what we just talked about last class, this is where that sort of explanation comes more in, your nitrogen, for it to be a good leaving group, you're probably going to have to protonate it first. So that's why acidic works out here. Then we talk about our haloform reaction and Strecker synthesis. Haloform, this is where we're doing it on alpha methyl ketones. We're using bromine and base, and we're progressively turning that methyl into a leaving group. Strecker is the really, really big one. This is the one where we're starting to bring together a whole bunch of different reactions. Strecker is the overall transformation going from our carbonyl, let's say an aldehyde. We're going to do an addition with some, usually ammonia, basically, and we're probably going to be doing it under acidic conditions. So we've got a balance of ammonia and the ammonium ion. We're going to be in addition to get us to our aminium intermediate, so it's that first condensation. These reactions are running in the presence of cyanide or nitrile, so we're doing nucleophilic substitutions as number 2. And then we're doing our hydrolysis. This is where we're adding water under acidic conditions to reformat that into our carboxylic acid. Just drawing it out as a zwitterionic form. Again, the really interesting thing about Strecker synthesis, we're chaining together a whole bunch of different reactions we've had starting back from lecture 1. We're doing our imine condensation, nucleophilic addition, and then finally hydrolysis, this last step of this hydrolysis of our nitrile from lecture 10. So it's a combination series of reactions. Most important thing, deep cleansing breath. Yes, please. So the acidic conditions for nitrile hydrolysis are favored, true. Your question is there conditions that basic hydrolysis, excuse me.
Yeah, or like, is there any specific conditions or like reagents that will only allow like the acidic version of the nitrile hydrolysis, but not the basic version?
Still don't think I get the question. So is there conditions that will only allow acidic hydrolysis of the nitrile, but not basic hydrolysis of the nitrile? I think, well, again, let me take a shot. Think of it like this. And again, I'm trying to come up with a question on the fly after weeks of drafting questions, so you guys are going to get something. Let's say we got that. Yeah, maybe this works. Let's say I got a molecule like this. So I've started off with a nitrile that has a chlorine in it, and I want to hydrolyze this group. And let's say I'm going to try doing it from sodium hydroxide in water, right? So I'm specifically setting this reaction up to do basic hydrolysis. That's the goal. All right, so basic hydrolysis here, I can probably hydrolyze this, right? That first addition, possible. The complication I might cite for something like this, in order to get this next step with hydroxide to do the hydrolysis of this group, it's going to require so much time, so much temperature. It is so hard to hit that nitrile. You are absolutely going to hit your primary chloride first in that case, if that makes sense. Is that kind of the sort of genre that you're asking around? So I think the way to think about it is, the thing with nitrile hydrolysis, that first one is at least possible. The second one requires so much energy that any other basic group would probably get knocked out also at the same time. I think that definitely would sort of fit. Similar to what you'd see with the Clemenson and stuff like that too. Okay, yes? In the end, yeah, you probably knock them both out. My point is, this is a molecule you would probably not want to try doing basic hydrolysis on. That's all I'm trying to set up. Make sense? Yeah, if you had to hit this one, if you really, really had to, it would have to be an acidic hydrolysis because you've got a base-sensitive group. That's how I'd sort of rank it. Okay, so the main things to go over right now. If you haven't already written a bunch of OChem type 1s, and based on the practice questions that you're going through, the main things you have to start off with is look through the entire exam. The way that the exam is set up is exactly what you've seen in the midterm sort of practice sessions. You've got a series of multiple choice questions, a series of medium long answer, and a series of long answer. Now, depending on your own study skills and what you like, you may be way better at some types of questions than others. Do not do it linearly if that's dangerous for you. You have 75 minutes. I've tried to time it out so you have plenty of time, but one of the first things I see people getting stressed out over is you spend a ton of time on page 1 because there's a lot of stuff there, and then a ton of time on page 2. And if you look at it, those are probably worth 1 or 2 points, and the last couple questions are worth 20. Space your time, right, is the basic point, right? So take a first step, look through the entire exam, and make a plan. Understand what the questions are, break it down, and make sure you pace yourself. That's always the first point. Second is read the question carefully. If I get, during the exam, one person asking this, Jason, where on the periodic table is this element? Hey, I've been teaching for a very long time, and every second year midterm, this happens at least once, but I'm stating explicitly now. You laugh, but come on. My point is, there will be things that may trip you up. You will get panicked. Take a breath, read the question. If it looks like it's something that's impossible, take a step back and say, you know what? Maybe what is the question asking me? The number one problem I get is somebody sees a question where all I'm saying is, which anion is more stable? And everybody gets like really distracted by, I've never seen an anion that looks like this before. What's going on over here? Stop. Again, if it looks like it's something that's absolutely impossible, guaranteed, go back, read the question. You're going to see something that actually helps you out. Don't get stuck too. What I mean is there's a lot of questions on this one. What can happen a lot of times too is if you're working through and you hit a certain question that's really bugging you, let it go, come back to it. We are in the first half. This is midterm 1, only 11, 12 questions, or only 11, 12 lectures, right? There's not that much content in the grand scheme of everything, which means a lot of questions are going to be based on similar topics. There are going to be times where I guarantee you, if you don't know the first part of the question, maybe there's a thing where you're like, I'm down to 2, maybe I don't know what it is. You can sometimes go through the exam, find another similar question that will remind you, oh, that's how I do this one over here. The exam is a finite brick of stuff you have to do, and there will be pieces that are going to help jog your memory in a later part of the question. So stop, move through it, and come back. It's always worst thing to do is get stuck and bogged down where you waste too much time. The back of the pages can be used for rough draft, but we only mark what you guys mark. Again, if there's something where you're working through and you have a sudden change of mind of what you want to do, you need to tell me clearly what your answer will be. If you need to recopy or change something else, I can give you more pages. But it's, if you're trying to answer on the back of your pages and you don't tell me that's where the answer is, I may not be able to grade it. So it's important to focus on that part too. So it means come up with a plan as you're going through it before you sort of like launch into it. Again, a lot of this material too, especially with the long answers, this is a way for you to communicate what you're thinking. I have to go through and mark these as, again, evaluating what your compound are. This is not a yes or no sort of answer of, you know, which is the most acidic or basic. Those are the first ones at the very beginning. Later in the exam, though, this is your chance to start writing down things like, I think this is an enolate, so I'm going to show you my acid and base chemistry, and then I'm going to show you my nucleophilicity. So leaving things blank is an easy way to definitely, there's nothing I can do to help you there. But if you've written down at least a concept of where you're getting going, starting into it, it's a much easier way for me to find ways to give you guys part marks. Big ones as far as structures. Again, if this is something you haven't been practicing through, if up until now, how you've been interacting with the questions is kind of like, okay, what's the question? You look at the answer. Yeah, I probably would have gotten that. That's not an effective way to engage with it because especially for drawing out structures and things like that, there's a certain amount of just practice that goes into, okay, I'm doing a functional group transformation of this nitrile, but I've got the rest of this molecule I have to bring along for the ride. Redrawing and recopying molecules where you delete atoms, that you change stereochemistry, that's the number one thing that really drops different parts. Watch your structures in terms of charge, especially for mechanism, is going through and making sure that you've actually got full bonding rationale. And pay attention to the species in the solution. Acidic and basic properties are the things that are there. Again, some of the weirdest ones I've seen is a multi-step transformation where atoms just get invented. Suddenly chlorine shows up for no good reason, and there's a phosphorus in your product that you never had that as a reagent. Again, marks for creativity, but doesn't help. You're not allowed to do alchemy. Okay, quick review of these functional groups. Do you remember their names? What's that?
We're given a question on the midterm that is like a nitrile hydrolysis under basic conditions. Would we, and we have to predict the product, would we write the amide or the carboxylic acid?
The best I could say is make sure you read the question, and I'll try to tell you what I'm after, right? If the question is, again, that's right, I hate saying anything in a blanket point, but best is read the question, right? If the point of the question is, you've been given these conditions and damn well you're going to hydrolyze it, and I'm asking you what might go wrong, you understand that component of it. The goal is if I'm doing a hydrolysis and there's some ambiguity in that sort of case, I'll probably give you a formula to try and get you to where the product is. So if I'm asking for a mechanism, get to the acid. If it's a, well, you didn't get the acid, what happened because of this, right? So the best is, again, read it, yeah.
About the pKa's, how many of them do we?
Good question, I'll answer that. Okay. Everybody, one creepy voice. This one is called a imine. Cool. This one is called a enolate. This is your, yeah, we just did that one. This is your enamine, and that's a hemiacetal, right? If you go through these, again, other components, secondary, other component, those are part of the other structures too, main categories. Who's the most, oh no, let's do this one. No, I don't want to do that. It's going to be too hard. But one of the questions that came up, hey, Jason, you gave me a list of 45 pKa's. Which ones do I need to memorize? All of them? No, but no. Look at it this way. That's the simultaneous jerk move. But look at it this way. And I've mentioned this to a couple people, so I just want to make sure I'll make it explicit. I look at the pKa scale, especially right now. You want to be able to break the pKa scale into buckets that you can represent certain groups in certain areas by certain pHs. You want to be able to break it up into regions, not exactly the entire sort of part, but have a couple representative structures. What I generally do is I think of 0 is down here and 45 is over there. And I'll break this out into less than 0, right? Then you've got 5, 10, 15, I call it 20 to 25. And then we've got 35, and then up here at 45. That's a terrible job spacing, but you get the point. Give me some functional groups, examples of functional groups that would be down in the less than 0. What's in this bucket over here? HCl. What else? Yeah, super strong acids, HCl, phosphoric acid, H3PO4, right? Also, pretty much what I'd call protonated oxygen species, right? This is protonated alcohols. This is protonated ketones. All the protonated oxygen ones are somewhere down below 0. Think of like H3O+, right? Okay, 5. What's in the neighborhood of 5? Yeah, these are your carboxylic acids. No problems. 10 is, yeah, these are your protonated nitrogens. Right? These are things like protonated amines, ammonia, things like that is in that range. 15 is, yeah, this is your neutral alcohols, not stabilized, not carboxylic acids, just normal alcohols are kind of in and around that 15. Water, H2O, is in that range. 20 to 25 is These are your alpha protons, right? This is where you're making enolates. Stabilized carbon anions are up in that kind of range there too. 35, yeah, this is your neutral nitrogens. Not protonated nitrogens, neutral nitrogens, to make that kind of fun. 45 is what? Yeah, this is like methane, right? This is neutral hydrogen that has to sort of do deprotonations here. The reason these buckets matter is because you can start to break down, like what we've done on the reactivity scales for the carboxylic acids. If I had something like butyl lithium, that's the conjugate base of my butane. That's 45. Butyl lithium is so basic, I can access everybody on this side, left of that. LDA is the conjugate base of my amines. It's in that 35 range. So that should inform you that LDA can do everybody on the left, but you can't rip off protons from butane. And then down, if I had things like enolates, things where I'm deprotoning the alpha center, I form those from stuff that's close by from that. It means I can't use carboxylates. I can't use the conjugate base of a molecule like this to form molecules like this. The bracketing we have here has helped to give you some sort of guidance in terms of relative reactivity. That's what matters. The entire pKa table I've provided gives you a bit more granularity. So for example, carboxylic acids are 5, but if I put a bunch of chlorines alpha to the carboxylic acid, which way does it go? Higher or lower? Lower. If I put a bunch of electron donating groups alpha to my carboxylic acid, it goes. So the way that you should start looking at this now is have some absolute reference molecules along this line, and then have some ways of modifying where that goes. And alcohol is around 15, but phenol, where you've got aromaticity, it slides down to 10, right? That's the best way to kind of learn this point for now. So you don't have to memorize 45 pKa's. I will never ask you a question of like, what's the pKa of that sulfate? My general rule, what I'm trying to do more than anything else, I will never ask you a question that you could Google. That doesn't make sense. All right, what about this? Which of these is the most reactive electrophile? And rank them from 1 down to 5. Okay, we're going to do this by vote with your clap. So if I circle the molecule you believe is the most electrophilic, I want to hear claps. Okay, so here, here, there we go. All right. All right. Number 1, I think we're going to go with that. Everybody agree? What's number 2? If you had to pick it, describe it. Yeah, it is. Oh, this one here? You know what that one's called? Does anybody else know what it's called? That's formaldehyde. And you know it's formaldehyde because you can see like a little bow tie on it there because, you know. It's not casual aldehyde, it's formaldehyde. Boo. Okay, yes, yes. Formaldehyde. What's next? Aldehyde. Which is aldehyde? Left extreme, yeah. This is number 3. Then what? Ketone. Is this an electrophile for any intents and purposes? If I try to take a carboxylic acid and I give it a simple base, all I get is no reaction apparently. No, it's acid and base. So not really an electrophile by any stretch of the imagination. It's a good acid, but it's not really electrophilic. Okay, let's practice deuterium. Oh, I love that sigh. Your tears, they're delicious. Okay. The strategy behind this question, remember, this is this example of when you're working through these questions and you're practicing them, and again, I'm giving you an example. This is how I learned this stuff. That's why I subscribe to that kind of 4 steps, or the different steps, the things that you should be writing down is number 1, what is the question asking you? Number 2, where is this question from? Number 3, how are you going to answer it? You want to kind of structure your answer around those pieces as you go through it. So, what is the question asking you? What's another way of phrasing what this question is asking you to do? Yeah. Sorry, a little louder. Yeah, like in the end, you're looking for reactive centers or stabilization of either positive or negative charges. You're looking for, can it make enols or enolates? It's really what you're talking about is which hydrogens are going to exchange, or which hydrogens are at alpha centers that can be supported by my carbonyl. Okay, where is this from? Where's a question like this we discussed? Do you remember which lecture? This is lecture number, yeah, it's like lecture number 6. This is our HD exchange stuff. Oh, it's lecture 8, right? Okay. How are you going to approach it? Now, in these conditions, I'm giving you acidic conditions because I'm asking you to look at how do you tautomerize, or which protons can exchange during tautomerization of the keto-enol tautomerism. The same centers that exchange under acid are the same centers that will exchange under base. So if you prefer, if you have a mnemonic, or you actually like sort of looking at this as anionic exchange instead of cationic exchange, you will find the exact same centers. So there is no difference between HG exchange centers under acidic or basic conditions. Right? So that's the way that you can sort of do both. The reason why I like using basic conditions is it helps me, and again, I'm really focused on things like stabilization of anions. The pKa charts really help you out here. So I'm going to do this assuming I'm allowed to deprotonate. Again, I'm using the basic conditions, but the answer is identical under acidic or basic. What I mean is, I start off with these 2 protons here. And I ask the question, if I were to yank off that proton and make a negative charge, is that negative charge resonance stabilized back to my carbonyl? Yes or no? Yes, that negative charge is nicely resonance stabilized through here. I could have at that center delta minus, which is also delta minus up here. For that enolate, that means that, yep, this center will exchange. Any protons at that center can exchange. So it passes the test. And now I can walk through every CH2 in the molecule and play the same game. If I was to deprotonate here, yes or no? Remember, that is a negative charge adjacent to it, both sides. CH2, oh my gosh. CH2 and CH2. Those are sp3 centers. There is no resonance available. I can't do this and I can't do this, right? So that one's not going to exchange. All right, let's go around to this one. If I was to deprotonate this center, make a negative charge, can I stabilize that negative charge by resonance? Yes or no? Yes. Okay. So let's do this one step further. If I was to take that charge and I just do this hop, right, it's all the way stabilized back to that carbonyl. So that means that, yeah, that center is in play. That center can exchange because even though it's remote, it's not immediately on an alpha center, it is connected to the alpha center by way of the double bond by resonance. Effectively, it is an alpha center. It's been promoted to that because you've got this molecular resonance between the 2. So one way to draw that resonance structure would be like this. Double bond, double bond. Remember, you have one more resonance structure in between. Where the negative charge exists here. Because of this extended system, you have 3 centers. It is delta minus here, delta minus here, delta minus there. This is the property of these resonance structures, right? Is they hop 1, 3, 1, 3 all the way through the system. basically what I'm saying for that is any center you see a delta minus on is in play. In this case, there are no hydrogens right here, but if there were hydrogens there, they could exchange because I have a resonance structure that supports a partial negative charge that could be protonated at some point. So what you're doing, and that's why, again, I'm showing you what would happen assuming this is basic. The exact same rules apply if you do cationic, right? The same rules apply if you work through the cationic structure. It's all based on the same sort of component. I like using the anionic ones because I think it's more illustrative, but this is how I sort of do this, this component. So what it means is, yeah, that bottom center will exchange. This is also deuterium. And then we keep going around. So this center, yes or no? Yes? Ooh, okay, we'll come back to that. This one? This one? This one? Yeah, that one for sure. Let's play this game. Well, no, I might be wrong. I just don't see it. Yoink. Again, this is the nice thing about drawing it out is you can get, if I was to go here, I'm going to make a negative charge. So let's use that one authentically. Negative. All right. Negative charge. What do you want to do for resonance? And then what? Down there? Right? Double bond, negative, right? Okay, resonance. Does that resonance structure connect to my carbonyl? I got resonance. That's a really crappy resonance. That will not help you. You're looking for resonance structures which connect the anion back to the carbonyl. Those are the low energy ones. Yes, that is more acidic than any other in here, not by much though. So that will not help. Okay. I've got one more one that I will do. I'm going to do this one online for you guys, longhand. I'll see you guys on, I guess, Tuesday. See you guys later. Okay, so for this question, what we're asked to do is draw the product and, again, pay attention to stereochemistry after we do a reduction. Now, what you should notice is this center here, that's a hemiacetal, which means there's an aldehyde based in here that the reduction is going to take care of. It's going to reduce. So the product we're looking for here will end up becoming a primary alcohol because effectively we're reducing what is the aldehyde center in this case. Now in order to do this, we want to draw this out in line bond structure. We're trying to get to something where we have normal wedge and dash notation. So the manipulation I would do here, step one, let's redraw this in sort of our normal line bond, but drawn in a hexagon way. So imagine you're viewing it down from the top like this. What I can do is that oxygen here corresponds to this oxygen. Carbon 1, 2, 3, 4, 5, and 6 corresponds to 1, 2, 3, 4, 5, and then sticking out of the ring will be carbon 6. Now I want to transcribe the geometry effectively. So if you imagine viewing down from the top in this geometry here, what we do is we go through each center, carbon 1 through carbon 5, and we pick if in the geometry we've drawn, we would be looking at that center as either a wedge or a dash. So starting here, if I view this center here, and I'm looking down from the direction I've seen at that center, I'm trying to draw with my blue arrow here, you can see what's going to happen is the hydrogen will be coming up towards you, and that means the oxygen is in behind to the back, like this. Okay, moving to the next center, I'm going to go to carbon 2. Once again, looking from the top, the first thing that's going to be pointing out at me is the hydrogen, and then in back is the oxygen. Again, that's the relative position over here, because remember, there's an axial hydrogen sticking up. Viewed from the top, the hydrogen is pointing towards me in that one. We go around each center in the same way. So carbon 3, we're going to have the oxygen sticking up, hydrogen back, and then carbon 4, it's going to be oxygen back and hydrogen up. And then carbon 5, that's actually going to have the carbon up to carbon 6. sticking up, and hydrogen to the back. And finally, the carbon-6 just has an OH. There's no chirality on that one because we have a CH2. Okay, now that we're drawn out correctly this way, next step is we want to open up the hemiacetal form over here. We're going to give it back to the aldehyde. So let's imagine we eliminate water, or we just open it back up to the ring. We would draw that as the OH, and we're not changing anything else quite yet. It's just the aldehyde at that center for right now. It means at each other center, we're destroying this chirality, so the oxygen at the back is now becoming this OH. But let's leave everybody else on there. And for now, I'm only going to draw the centers. So carbon-6 is sticking up like this. This is 5, 4, 3, 2, and 1, where I'm going to eliminate the hydrogens just to make it a little easier to see for right now. So OH, OH, like that. Cool. So now this is my open chain form of this compound. So now that we've got it set up like this, what we want to get to in the end is something kind of like a line bond type structure, where right now you can imagine as it's sitting right now, the carbon skeleton is kind of curving back on itself, and we want to get it sort of stretched out in a line, which means we're going to go through and rotate some of these bonds, which is going to help to align it to give us this linear kind of structure here. So really remember, we're not changing any center from R into S as we do that. What we're really doing is just rotating bonds to kind of change the geometry that they're being shown as. So in order to get this to line up a little bit easier, one of the first things I would do here is sort of take it in the middle, this bond 3 to 4. If I rotate about that one, I can kind of unwind things a little bit more. So let's just draw out what that would look like. So if I just did this bond rotation between 3 and 4, my aldehyde is still sticking up in this direction here. This goes down. Bond 3, 4 is still up like that. And then now this 4, 5 bond will be down in plane. And finally out to number 6. So 1, 2, 3, 4, 5, and 6 is what my intention is across that. Here, let me just move this over just a little bit. And now we have to add the functional groups back in. So carbon 2, we didn't do anything to it, still sticking back like that in that position. Carbon 3, same thing, still back in this position like that. Carbon 4, though, because we've rotated it, we took this oxygen here, which was to the back. If I rotate it, it's going to now be sticking up like that. So again, rotation around that. That means carbon 5 goes down, and we're kind of squishing down the center as well to make it in line, which puts carbon 5 would be back like this as the OH, and then carbon 6 is the OH out like that. Again, so you're doing two things in that move. You're rotating this bond here, and we're also squishing this one flat so that the carbon skeleton is in line instead of up like this. So imagine pushing down the center. The other way you could draw that center in that way, make it a little bit more obvious. If I were to take that here, so I'm pushing carbon 6 down into the plane, that means that this one, OH, is going to pop up like this. That's how, when I rotate about this bond here, this OH being up is now going to end up back in the plane of the page. So really, it's just the we haven't inverted R or S. All we're doing is the presentation. If you're ever confused about these, once you're in this geometry here, you can also assign the CIP rules to the center, and then that'll also help to make it more obvious. So now that this geometry is set up here, if you want it to get into a straight line, all we need to do is one more rotation, in this case about this bond, to help to get us into a fully linear structure. So redrawing that now, let's put that up here, would give me my OH out at the end, and then carbon 5 is back, OH, and then up, OH, back there. And then now that I've done that rotation, this one would be up again, down, and carbonyl to hydrogen. So numbering those centers off, what we've done is carbon number 1 is still here. This is 2, 3, 4, 5, and 6. Where again, really what I've done here is just by rotating about this bond, that's the back, it's now presented up to the front, and the aldehyde is now pointing down over here. That's the presentation that gets us in the linear structure. For the reaction, what we're doing is I'm going to reduce the center to its alcohol component. So I'm adding a hydride, sodium borohydride, to it to get us to the product seen here. So for this question, we're asked to react this molecule. All you have is what you see here. You're using a sodium hydride as a base. You should recognize this center is kind of like HWE kind of reagent, and over here we have carbonyl. So this is an intramolecular olefination reaction. So we're making a carbon double bonded carbon. So mapping out those centers, right? This here is my carbon nucleophile. That's where I'm going to make my negative charge. And then my electrophile is the center over here. This is my delta plus. So those are the new bond I'm going to form here is between carbon number 1 and carbon number 2. The rest of it is along for the ride. So we have 3, 4, 5, and 6. Now, why did I pick that one far away? The carbon right next door is in resonance. That's not my electrophilic center. So what I'm doing from here is I'm making a 6-membered ring. That's the first step. And if we map out the pieces, I'm making a double bond between carbon number 1 and carbon number 2, right? Those are the two centers that we're going to be reacting between those two. So let's map those out. I'm going to say carbon number 1 is this one up here, carbon 2 there, 3, 4, 5, and 6. Now that you've got your atoms numbered, now we can add the pieces into them. So if you follow this through, remember the way the HWE works, bond forms between 1 and 2, and whatever else is attached to carbon 2 is still going to be present. There's still a methyl group that was attached there that's present. And then carbon 3, 4, 5 is unfunctionalized. Carbon 6 has a carbonyl, which gives you this molecule here.